Welcome to my Chemistry 3400 students Summer 2020. This video is to overcome the difficulties that we went through yesterday during the WebEx section. We started by reminding you that the family of carboxylic acid, when you are naming the substances, you do not need to say what is carbon number 1 because according to IUPAC, similar to what we do with the family of aldehydes, the carbonyl is carbon number 1. So we know that this is carbon number 1, similar to what happens to the family of aldehydes. It is 4 carbons long, and the name of this substance is butanoic acid. Now we have a 7 carbons long carboxylic acid, therefore will be heptanoic acid, but now we have a substituent in carbon number 5. The name of this compound is 5-amino heptanoic acid. We spent a little bit of time discussing the different kind of carbons that will be important for biomolecules, and regarding the alpha carbon, we have a full chapter about it, but I don't want you guys to forget how important is an alpha carbon because we're going to see the acidity of the hydrogen bonded to this carbon. Also, we will look for what is the beta carbon, and we will discuss what is the omega carbon in the chapter of lipids. Besides the chemistry of the alpha carbon, in this class we are going to invest a lot of time exploring the alpha carbon of amino acids. We describe amino acids as the building blocks to make polymers of amino acids that we call proteins. In an amino acid, we will find that attached to the carbonyl, we call the alpha carbon, we will always have a hydrogen, an alkyl substituent that could be with different functional group to bring versatility to the protein, an amino group, and a carboxylic acid group. We're going to say that these substances will be chiral with only one exception, and that would be the amino acid of glycine. This carboxylic acid group is going to react with the amino end of a second amino acid to create what we call a peptide bond. When we have the formation of many peptide bonds, we will call that to be a polymer of amino acids that can fold in different ways to create a protein with function. This is just to present 3 examples of amino acids with different R substituent on the alpha carbon. We have one that is the small called alanine. It's going to be one that is a nonpolar substituent, one that is anacidic, has a second carboxylic acid group, and one that is a basic amino acid that is called lysine. We said that we have 20 different amino acids that we need to practice for biomolecules. Observe that the 3 amino acids that I'm presenting, all of them keep the alpha hydrogen, that the only difference in all of them is what is the R substituent. We call this chapter the chapter of carboxylic acids and derivatives, which means that we can make from carboxylic acids esters, anhydrides, we can make acyl halides, we can also make amides. But the fact is that carboxylic acids are very unreactive because the OH is a poor leaving group. So we make a more reactive compound like is an acyl halide that can help us to do the synthesis of esters, amides, and so on. Carboxylic acids undergo nucleophilic substitution reactions, while aldehydes and ketones undergo addition reactions. Because oxygen is more electronegative than the carbon of the carbonyl, we can place a partial plus charge around the carbon and a partial negative charge on the oxygen, and then the mechanism will be adding to the carbonyl. Then we will have the creation of a tetrahedral intermediate. To collapse the tetrahedral, the carbonyl reforms, expelling out the weakest base. Acyl chlorides are highly reactive to make other carboxylic acid derivatives because the chloride ion is a weak base, as it is the conjugate base of a very strong acid, hydrochloric acid. Please remember that you guys need to review chapter number 2 to have clear understanding of the properties of acids and bases, and I'm going to just overview what we discussed as what are the factors that will influence the acidity of a hydrogen. And that includes what is the electronegativity, what is the hybridization of the carbon, what is the atomic size, and resonance structures. We begin by looking at the electronegativity values of different substances. Oxygen is the most electronegative atom, has a value of 3.5. Nitrogen follows, and carbon is the least electronegative atom. Therefore, it will be much simpler for oxygen to donate a proton than for carbon. We know that alkanes are unreactive because it's very difficult to remove a hydrogen from an alkane. These examples can help us to illustrate how we are increasing the acidity of this hydrogen by replacing 3 hydrogens with an electronegative atom such as fluorine. When the bond order of carbon-carbons increases, that also increases the acidity of the hydrogens that are attached to the carbon. And we know that the family of terminal alkynes are acidic. We look at the pKa values, and we know here methane, a pKa of 60, will be less acidic than a vinylic when we have an sp2 carbon. When we have an sp in the family of alkynes now, there is a lot more S character, making this hydrogen more acidic, simpler to donate to a base. One factor that increases also the acidity of a substance, that will be the atomic size. In the example in here, we see that hydrogen iodine will be more acidic because we are increasing the size of the atom from top to bottom in the periodic chart, and that will increase what we call the polarizability. That means that the electron distribution around a iodine is a lot greater than what will be in the atom of fluorine. The last factor influencing the acidity of hydrogens is the resonance structures possible to obtain on the product. And we will see that, for example, here we have the molecule of ethanol that has a pKa of 16. It will donate a proton to a base, producing a negative charge on the oxygen that is localized. When we compare alcohol and a phenol, we also obtain phenoxide, which has a negative charge, but this molecule has the opportunity to have different resonance structures that will give stability to the substance. We could write more resonance structures so that we can see the electron delocalization within the carbons of the aromatic benzene ring. We can see that these 2 electrons are delocalized not only with the oxygen, but also in 3 different resonance structures. Once the proton is removed, we have a negative charge that can be delocalized, increasing the electron density within the ring. And that brings stability to this substance, making it more acidic than what will be for an alcohol. You need to go back to review resonance structures on chapter number 2 also. And in here I'm showing you guys how the hydrogen that is attached to a carboxylic acid group of a benzoic acid is going to be influenced by 2 different groups. One that is an electrodonating group that is increasing the electron density of the ring. If we have an electron donating group, the hydrogen is less acidic. It has an increase in the pKa. If we have an electron withdrawing group, that will decrease the electron density around the carbonyl and of course on the carboxylate group, making it more acidic. So we have a change of 4.46 increase and then 3.41 decrease. How does the electron density of the proton to be donated increases? The first thing is the methoxy group is going to donate the 2 electrons into the ring, and then we will have the electron being delocalized. We will see that we generate a plus charge on the oxygen after the creation of a double bond, and then we are going to pull electron density from the ring towards the carbonyl. We end up in all 3 different structures with the same charge. It's a charge of 0. We have a plus minus and a plus minus. Therefore, all of these 3 resonance structures are valid. With the nitro group, because we have a plus charge on the nitrogen, that will be pulling electron density from the ring, and because of that we're going to push electrons towards the oxygen. We generate a plus charge in the ring, decreasing the electron density of the proton, making it more acidic. The last topic that we introduced was the importance of the beta carbon, and also how the carboxylic acid groups need to be activated in order to work in biomolecules. And for activation, we say that we can do that in two different ways. I have a different video for that. We can say that the carboxylic acid group can be activated by formation of a mixed anhydride or by the use of coenzyme A that has a free thiol group to create a thioester bond. This is to remind you the importance of the use of the molecule of ATP to make a mixed anhydride, and that will be important for many chemical reactions.